Your DCS shows 238 degrees Celsius. The bimetallic gauge on the pipe says 215. Which one do you trust? By the end of this video, you will know exactly how to calibrate a temperature transmitter, sensor trim, output trim, and HART verification, so your DCS values stay accurate. Let us start with what the transmitter actually does. A temperature transmitter connects the sensing element in the process to your control system. The sensor, an RTD or thermocouple, sits inside a thermowell in the pipe. It produces a resistance or millivolt signal that changes with process temperature. The transmitter converts that signal into a 4 to 20 milliamp loop current. 4 milliamps is the lower range value. 20 milliamps is the upper range value. Your DCS reads this current and converts it back to degrees Celsius or Fahrenheit. Two sensor types are most common in process plants. The PT100 RTD changes resistance predictably with temperature. At 0 degrees Celsius, it reads exactly 100 ohms. At 100 degrees, it reads 138.5 ohms. At 350 degrees, it reads 213.8 ohms. These values follow the IEC 60751 standard. The thermocouple is different. It generates a small millivolt signal from the temperature difference at its junction. A Type K thermocouple produces about 4.1 millivolts at 100 degrees Celsius. You must configure the transmitter to match whichever sensor type is installed. In a process plant, temperature transmitters drift for several reasons. The RTD platinum element drifts over years of thermal cycling. Moisture entering the head corrodes the sensor terminals and shifts the resistance reading. Vibration from nearby pumps or compressors loosens connections. The transmitter's internal analog-to-digital converter also drifts with ambient temperature. At Parco, we routinely find transmitters that are off by 5 to 15 degrees after 2 years in service. Calibration restores the transmitter to within its specified accuracy, typically plus or minus 0.1% of calibrated span. For bench calibration of a PT100 RTD transmitter, you need 5 items. A decade resistance box. This lets you dial any resistance precisely, simulating the RTD at a known temperature. A loop calibrator like the Fluke 705. This sources and measures the 4 to 20 milliamp signal. A 24-volt DC power supply for the instrument loop. A digital multimeter for voltage and resistance checks. And for smart HART transmitters, the AMS Trex communicator, which connects across the loop and lets you run all trim functions from its touchscreen. Before starting, obtain your work permit and follow the site lockout-tagout procedure. For a temperature transmitter, isolation means safely disconnecting the sensor leads or removing the sensor from the thermowell. Check the area classification. In a hazardous zone, verify that all instruments and tools are intrinsically safe rated. Never open a transmitter head in a live classified area without the correct equipment. Confirm with the control room that the transmitter loop is in manual mode and the DCS operator is aware. Quick check. What resistance should you set on the decade box to simulate 100 degrees Celsius on a PT100 RTD? Think about it. The answer is 138.5 ohms. A PT100 RTD follows IEC 60751. At 0 degrees, it reads 100 ohms. At 100 degrees, it reads 138.5 ohms. At 350 degrees, it reads 213.8 ohms. These are the values you dial in during sensor trim. Connect the decade resistance box across the sensor input terminals of the transmitter. Set the resistance to 100 ohms. This simulates 0 degrees Celsius. Power the loop with 24 volts. The output should read exactly 4.000 milliamps. If your meter shows 4.12 milliamps, the sensor input is reading 7.5 degrees too high. That is an error of 12 microamps on a 16 milliamp span. Open the HART communicator and apply the lower sensor trim. Now set the decade box to 213.8 ohms to simulate 350 degrees Celsius. The output should reach 20.000 milliamps. Apply the upper sensor trim if needed. Run both points again to confirm you are within tolerance before disconnecting. Sensor trim corrects the input reading. Output trim corrects the analog output circuit. They are separate procedures and must not be confused. To trim the output, use the HART communicator to command the transmitter to output exactly 4 milliamps. Now measure the actual loop current with the Fluke 705 in measure mode. If it reads 3.98 milliamps, the digital-to-analog converter is low by 0.02 milliamps. Enter this measured value into the lower DA trim screen. The communicator adjusts the DAC automatically. Repeat the command at 20 milliamps and apply the upper trim. Never use output trim to mask a sensor error. That creates a false reading in your DCS. The AMS Trex communicator connects across the positive and negative loop terminals while the transmitter is live. No circuit break needed. From the home screen, navigate to Device Setup, then Calibration, then Sensor Trim. The communicator walks you through lower and upper trim steps. You enter the decade box resistance, command the trim, and the AMS writes the new calibration factors into the transmitter SEPROM. These factors survive a power cycle. When the trim is complete, generate the calibration certificate directly from the AMS. Record the as found and as left values. This documentation is your proof of calibration for the next audit. To summarize, a temperature transmitter converts RTD or thermocouple signal into a 4 to 20 milliamp output. Over time, the sensor input and the analog output both drift. You correct sensor input errors with sensor trim using a decade resistance box to simulate exact PT 100 resistance values. You correct output errors with DA trim, measuring the actual loop current with a calibrated milliamp meter. Smart transmitters store both trims permanently via HART. That 23-degree gap between your DCS and your local gauge? This procedure closes it. Thanks for watching. Subscribe for more instrumentation and OT content.